Welcome to ePathshala lecture series in computer science, and this is a course in cloud computing. Today we will talk about commit protocols. So, the agenda goes like this. We will see what is a commit protocol, and then we will go to see how do commit protocols work, what is a two-phase commit protocol, and then we will see it is also called a 2PC. So, we will see failures in 2PC followed by the summary. So, in the last class we saw what is a transaction and we looked at the acid properties of transaction, and we saw how to achieve the three acid properties. We were left with the atomicity in the last class. So, in today's class we will look at how to achieve atomicity in distributed transactions using a specific protocol which is known as two-phase commit protocol, or in short it is often called 2PC. So, let us quickly recapitulate what is a distributed transaction. The term distributed transaction refers to a transaction that accesses various objects in or even computation in different servers in a cloud environment. So, in the last module we saw that a transaction, whether it is distributed or a single server, has to follow what is known as acid properties, which are 4 properties in a transaction, and we saw how to achieve 3 of those 4 properties. This module we take care of the atomicity. So, what is atomicity? In a large distributed system like cloud, a transaction needs to be divided into smaller sub-transactions. As an example, we can look at a database will be updated. Maybe we have a big large data structure and we want to update it. Different parts of these data structures will be residing on different servers. Each such machine may be a server in the data center. So, these servers will be spread all over the place, and a transaction which will be updating this whole complete data structure have to access various servers to do it. Now, a typical way of doing this is known as atomic commit protocol. So, what do we have in an atomic commit protocol? Let us assume that this data structure that we are talking about, which requires updation, it is being initiated by some specific process. It could be the client also, which will be residing in one of the machines. Maybe it could be initiated by another server. So, let us also assume that there are 2 servers involved, P and Q. These 2 servers are residing in 2 different machines in a geographically dispersed locations, and both of them contain certain part of the data structure that we are talking about. Now, after the initiation by the server L or maybe a client process L, in P also some work will continue, in Q also some other work will be going on. When this distributed transaction comes to an end, or when it is time to complete the transaction, then the property of atomicity along with all the other properties, but the property of atomicity must be upheld. So, how to uphold the property of atomicity? We say that either both P and Q are ready to make all the changes, are ready to accept all the changes that it has made in its own part of the data structure, which is we call a commit in a transaction. So, committing means that the server is agreeing to accept whatever changes it has made, or neither of both of them should be saying that no changes are acceptable. So, even if it is acceptable, by P, if Q says no, I don't want to accept, then P also has to agree and say I don't want to accept. This is called an abort. So, in atomic protocol, let us assume that the transaction is interrupted by a crash. So, what happens if P crashes or any one of the servers crashes? So, if P crashes, within a certain time, it is expected that no cloud can afford to have a server being crashed for a very long time. So, within some time the server will come back up, and when it reboots, P's primary memory will be washed out. So, it will not remember what it was doing halfway. So, what we have to do is we have to make, to ensure that it does not forget, we have to take some expensive measures. Now, if P does not want to continue, how do we make Q to understand that P has forgotten? So, we are trying to abort the transaction, and Q has to also back out from whatever. So, whatever updates that have been done by Q must be taken out or roll back to the earlier value, so that it does not have any side effect of having a transaction being aborted. So, let us formulate the problem. A transaction has an unique ID, which is a TID. Every transaction must have a unique ID, so that any operation that is being executed should come with that unique ID. We will not confuse it with other transactions. So, to start with, the transaction starts as a pending state. It continues executing different operations. It acquires log for other consistency, etc. And then, if everything goes according to the plan, all servers have executed whatever they were supposed to execute, then they all commit. If something goes wrong at one or more than one servers, then all the other servers will discard the changes that have been made and everybody will abort. So, in atomic protocol, the typical way that we can think of is having a coordinator. We already know how to select a coordinator. So, we select one of these participating servers as the coordinator, and then we continue. The coordinator ensures that the outcome is same for all the servers. So, the coordinator depends, how the coordinator is going to depend, that is the protocol that we are going to talk about. We will have two protocols. One is called one-phase commit protocol and the next one is called two-phase commit protocol. Two-phase is the most commonly used protocol. It allows the servers to reach a joint decision. So, here is an example where this is the transaction. The transaction has write a comma 10, b comma 20, y write y comma 5 and write y comma z comma 7. Now, server P contains two objects a and b, while server Q contains the other two objects y and z. So, therefore, this makes it a distributed transaction, and the transaction has to access both the servers for executing these two all four instructions. Now, the coordinator in atomic protocol, the coordinator will take the final decision to abort or to commit. So, the coordinator, whichever is the coordinator, needs to know all the participating servers address, their basically IP address or whatever RPC if they are implementing. In turn, the participating server also needs to know that this particular server is acting as the coordinator. Now, the atomicity property needs to be implemented by ensuring that all the operations must be concluded in the same manner. So, commit or abort by all the transactions, by all the sub-transactions will ensure atomicity. So, the atomic commit protocols were first proposed in 1970s. This was a very simple way of ensuring that the atomicity is maintained. two-phase commit protocol was proposed in 1978. So, let us look at the first one, atomic one-phase commit protocol. The coordinator unilaterally takes a decision. So, coordinator starts, it waits for some amount of time, and then it decides that all the servers should commit or abort, and the coordinator then communicates its decision to all the participants, and the coordinator keeps on repeating this decision till it has not obtained a yes from or a agreement from all the participating servers. So, the coordinator does not have an option to to ask the servers, participating servers. So, it is therefore it is not a complete protocol, because the participating servers cannot unilaterally take a decision. Whatever the coordinator's decision, they have to accept. So, based on concurrency control issue, based on other things which are only relevant to one of the participating servers, the coordinator may not be aware of that, the server may not be able to commit even if the coordinator has taken a commit decision. So, this creates a problem in one phase commit protocol. Even a server crash may not be known to the coordinator, thereby making the decision very difficult. So, this problem is alleviated in the next commit protocol, which is a two-phase commit protocol. In a two-phase commit protocol, as the name suggests, it has two phases. In the first phase, each of the participants decide whether they are ready to commit. This decision is taken unilaterally by every participating servers, and they will communicate it to the coordinator, and in the second phase the coordinator decides based on the decisions of the participating server. It is a straightforward execution in case there are no failures, but unfortunately in a distributed environment failures will be there. So, therefore, many failures in fact are there. So, we can have server failures, we can have messages being lost, and we can also have a network partition by which servers, although they have not failed, they may be isolated from each other and not be able to communicate with each other. So, let us look at this two-phase commit protocol example. Here the coordinator contacts all the servers as we can see by the blue lines, and the servers will take a decision and will send the decision. So, the voting phase in phase 1, which is the voting phase, it will send a can commit request, and this can commit request to all the participants will be responded by yes or no by each participant. Yes if it can commit, no if it cannot commit. In phase 2, when the coordinator has obtained all the responses, then it will collect all these responses and will take a decision. If there is even one failure, it will say that if all the decisions are yes, then it will say yes. If one no, then it will say that do abort. So, either it sends do commit or it will say send do abort. Let us look at the reason why some of these participants can may say yes or no, but before that, if a participant says yes, then it will wait for the coordinator's decision, but if a participant says no, then it can directly go to the abort state, knowing that one no to the coordinator will cause the coordinator to take a do abort decision. So, in case the participant has said yes and the coordinator sends a do commit, then the participant says do have committed. So, this is the can commit coordinator is sending. So, we have one coordinator and we have a server P and a server Q. The coordinator sends a can commit to both the servers. The servers while they are taking the decision, they are receiving the coordinator scan commit message, the coordinator starts a timeout. This timeout is a very important mechanism in a two-phase commit protocol, because based on this timeout, the coordinator will decide. If a server fails to respond within the timeout, the coordinator takes a decision that it does not want to commit. So, all the server's responses will be saved in stable storage, and it will either say yes or no. So, we take it RP and RQ to be the responses of these servers. And in case the decision is yes, or in case it is no, the decision of the coordinator will depend on that, and the coordinator will send back something. Only after all the votes have been reached, so all responses must reach the coordinator, only then the coordinator can take a decision, or otherwise a timeout can happen. So, if both are yes and it has reached the coordinator before the timeout, then the coordinator takes a do commit decision and sends a do commit decision. When the servers receive the do commit decisions, they are already ready to commit. So, they say have committed, agreeing with the coordinator. In case one of the participants says no, the other participant may be saying yes, then the coordinator takes a do abort decision. No need to let server P here said no, so no need to tell server P do abort, only the server Q who was ready to commit gets a do abort message and it says OK. Similarly, for if server P says yes, then server Q does not get a response, server P gets a response do abort and it says OK. In case both say no, then the coordinator just takes a decision, writes in the stable storage and does not send any message to anybody. So, what happens when two-phase commit protocol faces failures? So, what are the failures that are possible? Any of the participating servers may crash. One or more participating servers can crash. The coordinator may crash. It is a single point of failure, as we have been saying in a distributed environment. Having a single point of failure is rather difficult, but it is possible, and any number of messages may be lost on the way. So, which message will be lost? No guarantee, but some of the messages may be lost. So, let us look at what happens when one of the participating servers crash. Each participating server is supposed to put their decision in a stable storage. So, in the first phase, after it gets can commit, it decides yes or no, writes in the stable storage and then sends the decision. In the next phase, have committed, it writes in the stable storage and sends the decision. Now, one or more participating servers may crash at any point in time. So, if a participating server has crashed, it is expected that it will recover at a later stage and will retrieve the response from the stable storage, and based on the response in the stable storage, it will take an action. So, what happens when it does retrieve? Now, if it fails before the initiation of the protocol, so coordinator has not yet sent a can commit and a participating server was using transaction and it fails. So, when it recovers, the participating server looks at its stable storage, does not find anything, so it will automatically assume that it is an abort. So, is it safe to consider that it is an abort? It is completely safe, because if other participating servers have said can commit without any decision from this specific server, the coordinator would have taken an abort decision, would have timed out, would have not received all the responses. This one particular server being crashed, it will not get the response from all n participating servers, and if it times out on even one participating server not responding, then in a two-phase commit, the coordinator takes a abort decision. So, the server that didn't receive a can commit, therefore, it did not take a decision on yes or no, can, when it comes back up, it can without any problem, it can safely abort. Is it possible that the server could have sent an yes? Perhaps, but since that yes has not been sent by the participating server, so therefore an abort decision is a perfectly fine decision and it does not cause any problem. Even if it does contact the coordinator after coming back up, the coordinator would definitely say it's an abort decision. So, no need to contact the coordinator, unilateral decision by the participating server. Now, if a participating node fails after receiving the can commit, but before deciding a yes no, so when it comes back up, it will check its stable storage and it will see that coordinator had sent a can commit, but its own decision is not there. So, what will happen? It will again abort because it has not sent a decision. So, no decision will be sent before putting it in the stable storage. If stable storage does not contain a yes or no, it means that it has failed before taking a decision. So, it will again, by the similar logic as we applied, it will abort. Now, if a participating node fails after receiving can commit and it may fail during deciding and writing in the storage, on recovery, what the server may find? It may find that a can commit and it's yes or no. Based on that, if it is yes, it waits, it looks for the decision from the coordinator. If it finds that it has a can commit from the coordinator and it has its own yes or no, but no decision from the coordinator has come, then what it will do is it will ask the coordinator, because with an yes it would have to ask get a do commit from the coordinator. So, while a failed participating node recovers, what about the other participating nodes? What are they doing? Very perfectly, other participating nodes do not have any problems. In all these cases, these participating nodes continue doing their work because the coordinator can take a decision if a participating server fails. So, we have no issues in distributed environment like cloud, we have no issues. Now, if a coordinator crashes, when a coordinator just like a participating server, it is just a server, so it can crash at any point in time. It is also writing all its decisions in stable storage. So, when this coordinator crashes and the coordinator comes back up, what it should do, let us look at that. Now, if it finds a do commit and have committed decisions in its logs, which means that it had sent a do commit and has received all the have committed, then no action is required. The transaction has already completed before the coordinator has crashed. However, if it finds that it had taken a do commit decision and but it has received maybe 0 have committed or a few have committed, not all the have committed from all the participating servers, what it should do, it will send the do commit once more. Now, it may be a resend of the do commit, but that really doesn't matter. It sends a do commit to all the participants and then waits for the have committed to come back and continues the normal activities. However, if it recovers and finds only the can commit and no do commit decision in its log, then it should typically abort and it sends a do abort decision to all the participants, because there may be a serious time gap between when the coordinator has crashed and when it has come back up. Now, since there is a time gap, let us look at what the participating servers are doing in the meantime. If a participating server has sent a yes to can commit and has not received a do commit, and finds that the coordinator has crashed. So what it can do? It can either just wait, or it can try to do what the coordinator would have done. Let us look at the other part where it is trying to mimic the coordinator's actions. Then it will contact other participating servers. If it finds at least one participating server which has sent a no, it aborts all the work. However, if it finds that all the participating servers have sent an yes, then it has to wait till the coordinator has come back up, and this is why this is a blocking protocol. So, this is the problem of two-phase commit protocol. This is one single problem point why two-phase commit protocol is called a blocking protocol. Now, if a message is lost, so what are the messages? Can commit message may be lost. The participating server times out, and will try again with the coordinator. It will abort if there is no, if it already has decided to give a no vote. Yes or no message may be lost. If yes or no message is lost, there is no problem. There will be a timeout at the coordinator, and the coordinator will abort the message, and it will send a do abort to all the participating. So, in case the do commit or do abort message is lost, then the server repeatedly polls the coordinator. The server will have to wait, a participating server has to wait for the message to be received, and no decision can be taken by the servers. Therefore, it is a blocking protocol. So, in a two-phase commit protocol is considered to be a blocking protocol because of the two incidents where if a specific message is lost, or if the coordinator crashes at a specific point in time, the protocol cannot continue. All the participating servers have to wait for the coordinator to come back up, and then only a decision can be taken. This may sound very simple, but the problem of this is that there may be thousands of servers that participate in a specific transaction, and all these servers cannot, at least one thread of all these servers will be stuck on this specific transaction, and the coordinator may take a very serious amount of time to recover. So, to alleviate this problem, the next proposal is a three-phase commit protocol. In this three-phase commit protocol, one more layer is added, one more phase is added, and using that phase, it is quite possible that all the participating servers can take their decisions unilaterally without ever waiting for the coordinator. But the more complex we create our systems, the more time it takes, and in many cases where there are no coordinator failures, all those additional phases have to be executed, and it does not make much sense. So, typically cloud like system which are very large, they do not opt for three-phase commit protocol, but all of them or many of them do take a two-phase commit protocol or a similar protocol. So, to summarize today's lecture, we looked at the distributed transactions and the atomicity property, and then we looked at an atomic protocol. What is a generally atomic protocol is to have a coordinator and let the coordinator coordinate with the servers. We specifically looked at two-phase commit protocol after doing a brief one-phase commit protocol also. In two-phase commit protocol, everything is fine, and work can be done very easily, transactions can be executed very easily. However, one specific case where if the coordinator fails at a specific time, then it may turn out to be a blocking protocol. To alleviate that problem, we may give add another phase to it, but it is not really required. In the next class, we will continue with our discussion of what happens when there is a replication and a transaction and what are the problems that can happen. These are our references. Thank you.